This is example 1 of 4 in a series of what I might consider to be semi-exhaustive electrochemistry problems. Things where you have standard cell potentials and Gibbs free energy in K, Nernst equation, stoichiometry, and everything else. So this is pretty much everything that could be asked in a standard galvanic cell. The only thing missing would be like an electrolysis cell. So let's take a look at this E standard cell. As a quick reminder, that's E standard for the oxidation and E standard for the reduction. Alright, so we need to figure this out. We have 2 reduction equations from some reduction potential table. We want to find a combination where we have 1 oxidation and 1 reduction that give us the number farthest right on the number line, ideally the most positive number. So I could flip this number, flip this equation, so that becomes an oxidation. I'd have negative 0.52 and negative 2.92, which would give me a negative 3.44. That's no good. So I'm going to have to flip this equation. And I think it's kind of important to show that so we don't get confused later. So we're going to have potassium turning into potassium ions and 1 electron, and as a result of flipping that, our E standard becomes 2.92 volts. All right, and as we look at this garbled equation over here, we have our reduction and we have our oxidation, and we just need to add those together. And so we end up with 0.52, and I guess I'll write that E standard cell. We've got, for our oxidation, 2.92 volts plus 0.52 volts, which gives us E standard for our cell of 3.44 volts. All right, so that's a standard skill. I think one of the first things you learn in electrochemistry calculations is calculating the standard cell potential for something. And then one of the first things you learn in redox equations, oxidation-reduction equations, or even regular chemistry, is balancing or combining these equations. This first example I picked is intentionally 1-to-1 stoichiometry with 1-to-1 electrons, so I will build in terms of complexity on that. So if we look at this, again, if this were a redox problem, we'd say, all right, we need to balance everything except hydrogen and oxygen for each of the half reactions, balance oxygen using water, hydrogen using H+, and everything else. In this particular case, since we have 1 electron already canceling out, then we just need to do some combining. So I tend to find it somewhat useful to identify visually, for me, what the reactants are going to be and what the products are going to be. In this particular case, we have Cu+ and potassium, giving us potassium ions and Cu, all right? And that is our balanced equation, all right? Like I said, I kind of picked a low-hanging fruit in this case. The other ones are going to get more and more complicated. To get a delta G, we need to utilize the Nernst equation, and I'll do the derivation maybe in another video, but for right now, delta G standard is negative N F E standard, where F is Faraday's constant, 96,485 coulombs per mole of electrons. And one of the things I tell my students, we're dealing with charges. Where are these charges coming from? They're coming from electrons. Electrons have a charge, and this 96,485 represents the amount of charge you get from 1 mole of electrons. So that's where that comes from. This N right here is our 1. If you're used to redox problems, combining those equations, you need to make the number of electrons match, because one equation is supplying electrons and one equation is using electrons. So in this particular case, this number here happens to be 1 electron. All right, so we can plug in some numbers here and find out that negative 1 mole of electrons times 96,485 coulombs per mole of electrons times 3.44 volts. Now, it's important to note what is a volt. It's a measure of electromotive force, cell potential, and that's measured in joules per coulomb, right? And I'm going to make this up, and I'm sure somebody will be offended, but it's kind of how much work moving those electrons moving can do, so we get work and a charge. In this particular case, 3.44 joules per coulomb from right there. The delta G right here for this one, negative 664 times 10 to the third joules per mole of reaction, right? Which a lot of times you'll see as negative 664 kilojoules per mole of reaction. And it's preference from whoever is going to score your stuff whether or not they want to see joules or kilojoules per mole of per mole of reactions. Now we need to start looking at our equilibrium constants. If you look back at thermodynamics, we know that delta G standard is negative RT, natural log of the equilibrium constant K, and that gets rearranged as K equals E to the negative delta G over RT. Alright, when you want to do that. Now, if delta G is negative NFE, then we can also say K equals E to the negative NFE standard over RT. And it's important that we note this sign convention. Positive cell potentials are considered to be spontaneous as written, and we may recall that delta G, the Gibbs free energy, is negative for spontaneous, so you get this negative sign right here. And that has to do with energy being done by the system, right, versus on the system. So it's from the point of view of the system. So in this particular case, delta G is going to be negative. It's going to be E to a positive number, just like here we're going to have E to a positive number. And we're going to find out that it's really, really easy for this number to get too big for your calculator to handle. And then you get an error. But that's fine, because that just means K is large. All right. In this particular case, we're going to have our negative 1 mole of electrons. Sorry about my spacing here. 96,485 coulombs per mole of electrons. This just got really, really ugly. 3.44 joules per coulomb. E to the, and then R, 8.314 joules per mole Kelvin times, and we'll just say at 25 degrees Celsius, never mention that, 298 Kelvin. Alright, so we end up with a K here that is large. In fact, your calculator will probably give you an error, but this is set up as error. Therefore, our K is large. Alright, for practicality, we can say that like the reaction goes to completion because K is pretty darn large. So the equilibrium lies far to the right. For part E, we're dealing with a non-standard cell potential. And just to jump back in time, when we calculated non-standard G, we did it based on the Gibbs free energy, the standard Gibbs free energy, and that was plus RT natural log of Q, the reaction quotient, right? So if we replace it with negative NFE and negative NFE standard, we get a slightly revised form where now we have E non-standard is E standard minus RT over NF natural log of Q. And you'll see this equation simplified a little bit, where sometimes you'll see 0.0591 over N log base 10 of Q. And that's an older form based on the time before calculators, when people would just look numbers up in log tables. For right now, we'll go with the natural log version, and that's going to be E standard, minus, assuming you have a constant temperature here, we're going to have 0.0257 over N natural log of Q. So in order for us to do this, we're going to need to know what Q is, and that's something that harkens back to equilibrium problems and even some of our thermodynamics problems. It's going to be products over reactants to their coefficient powers, and we'll look at our balanced equation up there. Q is going to be concentration of potassium ions to the first power over concentration of copper ions to the first power. Alright, so that's what we're going to use for Q. In fact, it might be worth our time to highlight that this is what appears right there. And you'll notice that I gave some K values, or sorry, some potassium ion concentrations and copper ion concentrations over there. And now we can knock out E and F pretty quickly, and then G with just a little bit more work. So in this particular case, our E non-standard is going to be 3.44 volts minus 0.0257 over our number of moles, which was 1 from up there. In fact, it might be good if I took that number and relayed it to those numbers right there. And that'll be the natural log of our concentration of potassium ions over our concentration of copper ions, which is 2.50 over 0.10. So 2.50 over 0.10. And so one thing to consider here is when you have a log, this number inside is going to be greater than 1. So in this particular case, the log of a number greater than 1 will be positive. So this whole term is going to remain negative, and this number is going to go down. So I'm predicting that my non-standard cell potential is going to be lower than my cell potential right here. And we happen to see this calculation as 3.36 volts for our E non-standard. And I want to look at that in a slightly different way, and that is, in terms of Q's and K's and equilibrium, we should, if you have standard conditions, the numerator would be a 1, the denominator would be a 1, this whole term would cancel out as 0, and E would be E standard, 3.44 volts. So the question is, what's going to happen with this term? Well, potassium ions are your product, and copper ions are your reactant, and if you look in this particular example, you have significantly more potassium ions proportionally, okay? So our numerator is bigger than our denominator. Our numerator is products. We have way more product than reactant. It's going to be harder to go from reactants to products in that direction. And I'll say it again in slow-mo. The driving force, if we have a 1 and a 1 here, gives us 3.44 volts. But this number is less than 1, so it's not pushing as hard in the product direction. This number is greater than 1, so it's pushing in that direction. It's harder to go towards products. And so this 3.44 has to go down, philosophically speaking. So once again, number bigger than 1 here, this whole term is positive, so this contribution is negative, this number goes down. The reason being, too much product, harder to go that way, harder to actually driving force that way. Alright, so that's two different ways to think about it. And that is letter E right there. Letter F is pretty much the same calculation, but we just change what's in there for Q. So our E here is going to be 3.44 volts again, minus 0.0257 over still 1 mole of electrons, same reasoning. And we've got then the natural log of our potassium ions, 0.050 over 3.0. So, think about this mathematically. The natural log of a number less than 1 is negative. So this is negative. This term becomes a positive contribution, and then 3.44 goes up. So I'm expecting a bigger number. In this particular case, it happens to be 3.54 volts for the E cell. And if we look at that once again, in terms of our, philosophically speaking, products, reactants, our products are less than 1, our reactants are more than 1, it's going to be easier to go that way. Alright, this number's 3, it's pushing harder than a 1 would. This number's 0.05, it's resisting less than a 1 would, and so that reaction goes that way a little bit easier. Now comes the time where we need to work in some stoichiometry for part G. And I'm going to rewrite this equation just because it's not in a convenient location, but we have Cu plus potassium giving us K plus copper. Alright? And I'm going to set up some stoichiometry here that looks a lot like ice, but it is going to be stoichiometry. And I'm going to take these numbers from part F, it says, alright? And I already lost that marker, so we'll just... So the potassium ions in part F were 0.050 molar, and the copper ions were 3.0 molar. Now, when we look at what it says here, take part F and lose 2.25 molar. So as the reaction proceeds, the amount of reactants are going to go down and the amount of products are going to go up. In this particular case, the reaction proceeded, this battery got used up essentially by 2.25 molar. So we're going to lose 2.25 molar, and it might be helpful if we took note that this number and this number came as that number and that number, and then this 2.25 was given right there. Okay? Alright, so if this is consuming 2.25 molar, it's one-to-one stoichiometry, and this has to go up by 2.25 molar. Alright? And we're not worried about just here the potassium metal, copper metal. Those are pure substance. They don't appear in Q, and I guess I neglected to mention that here. This is a solid. This is a solid. We're only worried in our equilibrium expression about aqueous and gaseous reactants and products. So as we look at this, we're going to end up with 0.75 molar copper ions and 2.30 for our potassium ions. And now we're just going to use this equation again. E is going to equal E standard minus 0.0257 over N, natural log of, in this particular case, for Q, K plus over Cu plus. And this is going to be squeezed in a little bit at the bottom here, but we got it. 3.44 volts minus 0.0257 over our N, which is 1. Natural log of our new numbers here, 2.30 over 0.75. Alright, and a quick glance here, bigger than 1, less than 1. So products greater than 1, reactants less than 1. Products greater than 1, resisting the transition from reactants to products. Reactants less than 1, so not pushing as hard that way. I'm expecting that number to go down. Also, this number is greater than 1. This component is positive. This contribution is negative. This number should go down. All right. In this particular case, we end up with an E for that cell. Sorry about that. An E for our cell of 3.41 volts, and it has gone down. The next the next three examples are only going to get uglier and uglier.